السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. This is, I think, although it's counted as the second lecture in the course, but I think this is the actual first lecture. The lecture last week, it was very brief, light introduction to the field, and you managed to stay in the course after that lecture, which is good. So I hope, inshallah, starting this lecture, you will learn much more than what you had in the previous lecture. Just as a warming up, as I used to do in some of my classes, some of the quick questions that we'll try to answer together. First one, is effectiveness more important than efficiency in IR? Yes. Yes, both are important, right? Both are important. Is searching for videos considered an IR problem?
Yes.
Yes. Okay. True or false? Relevance is having a value with respect to the query. Raise your hand, please. Yes. It's related to the information need. Very good. Okay. It's related to the information need, not the query, because the query is just the representation, the text representation of the need, but it is related to the information need. What is the difference between information needs and queries? What is the, yes? The information need is what the user desires, the task that the user want to do. Okay, so it's like the translation of the information need from your mind to the computer, right? It's just a representation that you enter through the or issue through the search engine. Okay. The last one, true or false? Indexing is done online. Yes.
False.
False. Why is that?
Because first we will index the document and then we'll make the matching online.
Very good, but that doesn't mean that so these are two steps in sequence, yes, but maybe they will be done online. Having a sequence of two steps doesn't mean that it has to be offline. It has to be online.
To improve the effectiveness, we should index the document and then we'll compare between the query and
So what happens if we do the indexing online? Can you imagine Google doing the indexing online? Thank you.
Very easy task because including the storing the data.
Yes, it's a huge task, right? And we don't need even to wait for the queries from the user before we do the indexing. Indexing is done completely offline, waiting for the user to give the queries. But it has nothing to do with specific query. The index is for the entire collection. Okay, is that clear? Okay. Any question about what we covered last time then? Okay. Then here's the roadmap for today. We'll start, inshallah, by what we stopped at last time, which is how IR sees documents. I think we didn't finish, the last couple of slides on that. Then we'll talk about Boolean Retrieval, which is the first retrieval model that we will, inshallah, cover in this course. Then we'll talk about special kind of queries called proximity queries and how we can support them. Then we'll talk about a special type of indexes called fields or zones. And then we will see how we can adapt Boolean retrieval to do also what we call ranked retrieval. Okay? And that will be it for today, inshallah. So the first part, which we started last time, is about how IR sees documents. And I think we started to talk about that, right? What was the main idea, the key idea from last time about that? Yes?
bag of words.
Bag of words. Okay, so what do you mean by bag of words?
The order of the words doesn't change the overall meaning.
The overall meaning. Very good. Okay. So one of the key ideas in IR, and most of the retrieval models in IR, is the idea of bag of words, that we present documents as bags of words. Okay? And what we mean by that is that we destroy the structure. Okay, we destroy the order of the words. We don't care about them because the idea is that the meaning will still will be there. Okay. Yes. Question.
Is this only applicable in the case of text or even applicable for the video, music?
That's a very good question. As I said earlier in the previous lecture, our focus will be on text. Okay, so not necessarily that will be applied in other types of data, but mainly we are talking about text. Okay, any other questions? Okay, so the idea is bag of words trick, and I think we saw these two examples last time. You manage it easily to get the order of the words in the first one. The second one was a bit harder, but still with some time you got it. So the topic here was there. So reordering doesn't destroy the topic. That was the main message, because actually the topic is a set of words and the words are still there. We didn't get rid of them. As I said, most search engines use actually bag of words, mostly for efficiency reasons, because it's very the implementation of it is very makes the retrieval models very fast, okay, and that's very important. And also it shows that we can get very effective results also. Okay, so it's both sides. And the idea that we can represent the document as a bag of words can be also applied at the query side. So we can also do that for the query, and we can represent the query as a bag of words, as we will see, I think, starting, inshallah, next lecture. We also introduced the notion of retrieval models. These are the main component of a search engine that will rank or will find or will match documents with queries, with given queries. And inshallah today we will start to talk about the first studied model, which is Boolean Retrieval. So as I said, bag of words makes these models tractable, and tractable here means feasible to implement, feasible to use, okay, in terms of efficiency, okay, and also effective, as I said. With that, there are of course some critical points about bag of words. So let's go through them quickly and see if they are really worth of our worries. The first one, word meaning lost without context. It's kind of true, but actually we don't discard completely the context, right? Because the context is still looking at the words together. We can guess the context. So the context is still kind of implicitly represented through the words. Okay, so we just discard the surface form, which is the structure of the sentence, but still the words are there, which are the main components of the context. What about negations? You know, negations, the order for negations is very important, right? So where the not is, or where exactly is this negation in the word in the sentence is very important generally. Okay, but look at these two cases. We have not climate change is real and climate change is not real. We changed the where the word is, where the word not is. Of course, it's different. Okay, but remember in IR we care more about the topic of the sentence. Okay, so still we discuss the same topic, whether the not is before real or before climate change or whatever. Still the topic is about the thing that without not. Okay, so we still have the same subject. Of course, that doesn't mean that it's completely fine. I mean, sometimes, of course, we lose something. Of course, we lose something. Okay, but in most cases, it works fine. It doesn't work for all languages. Chinese, for example, they don't have separators. They don't use spaces. I think also Japanese. Okay? So there is no word unit for some languages. So we cannot just say, okay, we will ignore the order because we don't know where the words are in the first place. Okay, that's not for processing. Okay, I can answer from processing from the IR perspective, not from the language perspective. In IR, we solve this by using what we call segmentation. Okay, so using an automated algorithm, we just chop the characters into smaller units. Okay, whether they are actually words or not, we don't care much. No, for English we look for spaces to separate between words, right? Whenever we have a space or commas or punctuations, we know that this is the end of the word, right? But in some languages there are no such thing. Okay, so for process, I don't know in terms of language how they solve it. I don't know Chinese nor Japanese, but for IR we do, for this kind of languages, we do what we call segmentation. So we actually divide it in some way, okay, so that we can deal with what we can call, not words, because we are not sure they are words, but we call them terms, okay, in this case. Okay, any question about this quick bag of words concept? Okay, we'll get back to it inshallah, I think 2 weeks from today when we talk about ranked retrieval. Okay, now we'll switch to the first retrieval model that we will inshallah discuss in this course, which is called Boolean retrieval. I think you are familiar with the word Boolean, right? What is Boolean? True or false, 0 or 1, right? Something that has two states. Right. How is that related to retrieval, to information retrieval? Before answering this question, let me ask you, should be simple question. Let's say that we have a collection of documents. I gave you a collection of documents, okay? Not formatted, okay? Just text, okay? We assume always that it's always text, okay? There's no special formats or anything. And I want to find specific words within, I want to issue a query against these documents, okay? I want to find the documents among this collection that are relevant to that query. Let's say that for simplicity, we assume that the query is just one word. Okay, forget about multiple words, just one word. And I want to know which of these documents are relevant to that query. What is the simplest way of implementation of this functionality that you can do? The simplest. The first thing that can come to your mind. Yes? Yes, so when we get the query, we start to scan the document word by word, document by document, and within each document, word by word, and check if that word appears in that document or not, right? So we call that kind of idea sequential scan, or grep-like, if you know grep in Unix. It's a command that does exactly this when you give it a word or so. So this is sequentially done, right? So we can go through the collection of documents, one collection at a time, read each word, and match it with the query, right? This is very simple. So we don't need search engines then. We know how to do it, right? So what is the problem with that? It's very simple, but very inefficient, of course, okay? If we are talking about 2 or 3 documents, 10 documents, 100 documents, maybe that would be okay. Okay, but going beyond that with the scale that we are talking about in IR, of course you cannot do that. Okay? Otherwise, if you imagine that Google will do that whenever we enter a query, I think we would wait for years, really years, maybe hundreds of years, until we just know which documents have this word. Okay, if we go and scan each document one by one. Of course, this is this is not efficient. But the question here is that whether this is effective. And let's say that it's okay to do that for a small number of documents. Will that be effective with the sense that we discussed last time? Would that be effective? And it will give us really good results? I like that you are very confident. Yes. يعني مفيش أي قلق إنه it might not يعني ها؟ Yes. Okay. طيب, this is your opinion. So it's very clear. It's word by word. We'll not miss anything, right? That's your idea. So of course we'll find the relevant documents. Any other opinions? And all of you agree with it? Yes. Very good. It's a query. It's a search query. Okay. So what should be the task here? It's about, yes. That's why I said relevant. It's not about whether the document has the word or not. Okay, it's not like find in Microsoft Word. Control F, you type the word and you get where the word is. I want to get the documents that are relevant to that query. Okay, so you can always think about relevancy, topically relevant, about the topic, as you said. So, again, any other opinions? Yes. That's a different story, but let's think about what we just proposed, is to go word by word and check the documents. Will that give us effective results or not? Yes. Okay. Okay, so that's the first problem. Okay, so maybe some documents will not have this specific word and they are still relevant. Okay, so that's one. Now we are saying yes. Okay, okay. Is that the only problem? No. We treat all yes, okay, so that's a kind of problem. We treat all documents that have the word equally, okay, so we cannot distinguish between them. Okay, there is more severe problem. One more severe problem. Yes, some words have different meanings, right? It's called in NLP different senses. Okay, like the traditional one, I think I mentioned it last time. The word bank. Maybe I didn't mention it. The word bank has at least two meanings, right? Bank, the financial institute, and bank is the river bank. Okay, so with this method, we'll always get whatever bank, and some of them might not be actually relevant to the information need. Okay, it might these documents might not be relevant. So it's sorry. It might know that you are working at a bank, and most probably you mean the bank, the institute. So it will at least put the documents that have the sense, the financial sense first. So there are many things here. It might, of course. It might. Okay, so it's not efficient. I think that was very clear. It's not scalable yet. And I hope that is clear now. It's also not effective. So the question is, how can we make it more effective and efficient? That's the whole course will be an answer to this question. But at least this simple first idea doesn't work in IR. Okay, it works with very small number of documents, and it will not give you actually good results. So what is Boolean retrieval model? In Boolean retrieval, since you of course know the word Boolean, the query, we will assume that the query will be written in Boolean expression. Okay, so you are familiar also with Boolean expressions, right? Like X and Y. X and Y or Z, right? So the query will not be free text query like what we write to Google or to usually we do with the search engines, but the queries will be written as Boolean expressions. Okay, so that's the first important point here, that the queries are not free text. What we usually write is called free text because we don't give any structure, right? We don't say this and that or this or that, right? We just write natural language queries. That's actually one type of queries. But the queries that we are talking about here are written in Boolean expressions. Okay? Fine. Boolean expressions, of course, use the three standard operations, which are and, or, and not, and of course you know the meaning of each. So, for example, the query Qatar and university and not street, okay, should return back what? What should be the outcome if I issue such query? What do you expect? If I tell you now, here's the query, Qatar and university and not street. Yes. Very good. Okay, so from that expression, I want the document that will satisfy this expression. So that's actually the idea of the Boolean retrieval model. The queries will be Boolean, and the documents that will be returned or retrieved will be only the documents that will match the query or will satisfy the query. Okay, if I evaluate the query with respect to that document, I will get true. Okay, as a result. So if that's the case, then I will retrieve such document to the user. So in this case, I will get or retrieve the documents that have the words Qatar and university, but not street. Okay, so it seems here that the topic is about actually Qatar University, but I don't want documents that are actually talking about the Qatar University street, because there is actually, you know, that the street also is called, I think, Sharia Jamia or something like that. So we might get documents like that. So I want in that, if I am the one who is issuing this query, I want to exclude such documents from the retrieved set. Okay? Fine. Here, the documents again will be viewed, as we mentioned, will be viewed as bag of words. Okay? So we will treat the documents as bag of words, which means that we will not keep, until further notice later in this lecture, we will not keep any order between the words. Okay? Fine. Now, this model should return back only the documents that satisfy the Boolean query as we said. Now, here's an exercise that I want you to do right now. We want to build what we call term document incidence matrix. What is this? You know matrices, right? It's like a table with rows and columns. Now, the rows will be the terms that are in the documents, and the columns will be represent the documents. Okay. I want to build that matrix for a given collection of documents. Whenever I say collection, you know that it's a collection of documents. Okay. So here in this exercise, we have 5 documents, as you see on the slide. And out of this collection, I want to build that matrix. This matrix, the words, forget about the word term now. Let's just consider that they are words. And so each row will represent one word, and each column will represent one document. Now, what is inside that matrix, actually? We will have 0 or 1. 0 if that word didn't appear in that document, and 1 if it appeared in that document. Okay, so let's do it together. How can we do this? So we'll go through the documents, right? Word by word. Very good. So let's do that. So we'll start with he. Okay. Okay. Now, one of the issues that we will discuss. Okay. Let me write it as it appeared. Okay. So he. Okay. So that will be the term, and let me do it like that for the documents. Okay. So okay. So he appeared in document. So we will present, we'll process document 1 now. Okay. So he then likes. Okay. Should we put 1 here? No. Likes appeared in document 1, right? Okay. What else? 2. Yes. We'll come back to that. Okay. We'll come back to that. 2. Okay. Then wink. Wink with comma or wink without comma?
What comma?
Okay, I will do it without comma now, and I will tell you the reason later. Okay. Okay. So wink without comma. Then he again. Did we see he before? With H capital or small? Okay. So that's a question, right? Is it the same here or not? It should be the same here, right? So it should be the same thing. We shouldn't have some another term called he with small h, right? Okay. So we'll just do it that way here, and we'll keep the small one for a reason that I also will talk about later. So all of these decisions are called pre-processing decisions. Okay, so these are decisions that we take when we do what we call pre-processing, when we pre-process the documents, when we chunk it into small units called terms. We'll talk about that inshallah later. Okay, what else? So should we do anything with he again, or that's enough? That's enough, right? Because we already put 1 here, right? Okay, what's next? Likes. We had it already, right? Okay. Then 2. We also had it. Then drink. So drink is new, right? So drink, we have 1 here. Okay. So we are done with the document 1. Okay, let's do document 2 quickly. He. 1 with document 2. Likes. We have it. 2. We have it. Drink. Drink 0. Okay, we are here, right? Okay, so I'm processing document 2 now. So do you see wink here? You don't see wink. So you see drink. So drink is 1, and again drink with comma or without comma. Okay, we'll remove the commas. And should we add and or not? Okay, and okay, very good. 0, 1, and what's next? That's it. Why is that it? Because drink appeared before, and appeared before, and drink appeared before. Okay, so we just need to add 0 here to indicate that it didn't appear. Okay, so we'll do that for the entire collection. Okay, now when we do that, so any question about this? Okay, we do that, we get this. Okay, so this is what we call term, document, incidence matrix. Why we call it that way? Because the rows are the terms and the columns are the documents. So that's the part term document. Why is it called incidence? Matrix, we know why it's called matrix. Why is it called incidence matrix? Huh? No, but the word incidence has a meaning. Yes. Can you raise your voice, please? Yes, so it's about occurrence of the term in a document. Okay, so that's why it's called incidence. It's 0 or 1, it's true or false, there or not. Okay, so that's term document incidence matrix. Do we capture any counts here? And do we capture how many times, for example, the word drink appeared? We don't, right? It's just incidence, occurrence, 0 or 1. Okay? Any question about this? Fine. Why do we need that? Just a silly task that we do together? Of course not. Huh? We know which what? But we know that from the collection, right? We have each document. This is the word that appears in that document. We already have this. We don't need the matrix. Okay, so this is a step that is very important, as you will see in the next slide, to match the Boolean expression with the documents. Okay? So here is a simple form of this exact matrix, just to illustrate the idea here. Now let's say that we have, okay, so let me define, give you some definitions here. We said that the rows are called words, right? But the actual definition for that is terms, because terms are not always words. Okay, and we will know that inshallah later. Okay, but you can keep it in mind now that it is like a word, but actually it might not be a word. Okay, but you can use the word now just for replacement, but it is actually called terms. And the columns, of course, are the documents, and each number inside the matrix is 1 if the document contains the term, and 0 otherwise. So that's the definition of the matrix. Now, if I have a query like this, wink and drink and not ink. By the way, if you read the documents, you will have fun reading the documents if you notice the meaning of them. But anyway, if we have a query now that is wink and drink and not ink, how can we find out the documents that will match this query using this matrix? Yes. Okay, so we'll search for a document that has 1 for wink and 1 for drink and 0 for ink. Okay, so that means that you need to know how can you satisfy this condition, this query, right? In whoever is taking algorithms now, I think you will algorithms course. I think you will go through satisfiability problem. Okay, whether this query is satisfied or this expression is satisfied or not. So what you said is that we'll have to go through every document, okay, and one by one, right? Who answered it? But we first, okay, there are 2 things here. First, that we need to do it document by document, right? So every column, we go through every column and check if we have 1 for wink, 1 for drink, and 0 for ink, right? Right? Okay. So that's first thing. Of course, the problem with that is that we have to go through all the documents, right? So that's huge if we have large collection. And the more severe problem is that we'll have to understand that we are looking for 1, 1, 0. It's easy because the query is easy now, right? But if the query is really big, it will not be easy to find out exactly the pattern that you are looking at. Okay? So here is one way of doing it. You will, instead of looking at the columns as you suggested, we will look at rows. Okay? So we'll find, first we'll retrieve the rows that correspond to the terms that appear in the query. So we'll get wink, we'll get drink, and we'll get ink. Okay? So we'll assume that we get now these rows, because we have the matrix, right? So we can get the rows, whatever rows that we want from that matrix, and then apply this expression on the rows, as we do in Boolean algebra. Okay, so the first will evaluate the expression, of course, based on the Boolean expression precedence order of operations. Here we'll have to do, of course, the not, and then we do the ending. But we can also start with the first and then do the second one. So we apply this query, this expression, on the rows. When we do that, we'll get the first sequence of bits here. What is that sequence? That's the sequence for the wink row. Okay, that's the sequence of the wink row. That's 1 0 0 1 0 0 0 1. Okay, and this is the drink row, and this is the ink row. Okay, and then we start to apply. After we do that for all the words that appear in the query, we start to apply the expression, to evaluate the expression. Okay, so when we evaluate this will give us what? Not this one. What will we get? 1 1 0 0 0. Okay, so now we get rid of not. Now we have all ands. So if we AND all of these, we'll get this one, which is 1 0 0 0 0. Now, what is the meaning of this one? What is the meaning of what we did? It's exactly like what you suggested, but all at once. Okay, because these operations, we know how we make this very efficient. Okay, because these are bits, right? So the bits operation for a processor is, that's the thing that it does. That's the only thing that it knows how to do. Okay, is to do operations on bits. Okay, so that can be done very efficiently. But what is the meaning of it? Yes. Yes. Okay. So this is like we evaluated the query for every document. Every bit here corresponds to one document, and it's completely independent from the others. So that's exactly what was suggested earlier, but doing all of them at once. So that means that the first one corresponds to the first document, and the second one will correspond to the second document, and the third one will correspond to the third document. Okay? So what is the result now? What should we retrieve? Document 1 only. Of course, it might, for other queries, we might get more than one. Okay, so this is just an example. It happened just by chance that we have just one document. But if we got, for example, 10100, that means that document 1 and document 3, in this case, will be retrieved. Okay? Any questions about that? Questions? Clear? Okay. Okay, is that efficient? Why not? Right, we'll answer this later, okay? In a couple of slides probably. Right, now, this is how Boolean retrieval works, regardless of the exact details of the implementation. But Boolean retrieval model divides the collection, given a query, it divides the collection into two parts. One that is matching this query, which will be retrieved to the user, or returned to the user, and one that is not, which will be ignored, will not be presented to the user, of course, because they don't satisfy the query. Okay, it might satisfy part of it, but it's not as a whole. We don't care. We don't care if it satisfies part but doesn't eventually satisfy. We care about the entire query, whether it satisfies the entire query or not. So that's why it's called Boolean here, because also because of its nature of having Boolean expressions as queries, we have Boolean division also. We have part of the collection that will be matching or satisfying, and the other that is not. Okay. And this is also called exact match retrieval. Why? Because it's either satisfying this expression or not. Okay, and it has to match exactly the expression. Does that remind you of something? What is it? Okay, but generalizing it now with a Boolean expression, does it remind you? Structure, which is done in databases. So in databases, we do actually exact match. When we search in databases, what we do is exact match, and we mentioned that last time, right? When we did this comparison. So this is very similar to what we do in databases, but here the difference is that we have text.
Doctor?
Okay. And that's the simplest model that we have. Yes.
Sorry to.
It has so many, of course, problems. Okay. Yes, spellings, of course, will be a problem, and there are also other problems like the same problems that we discussed in terms of effectiveness when we talked about this simple approach of scanning. Again, also maybe for some queries, the documents that will be returned will not be about or will not be satisfying the information need. They will be satisfying the query, by the way. Okay, for sure, they will be satisfying the query. Okay, whatever you write, you will get. But that doesn't mean that what you will get is actually relevant to your information need. Okay? Okay. Type. It has this problem, right? And also one of the disadvantages is that, as I think earlier mentioned, we cannot know which documents are more relevant to the query or to the information need than others, because it's just a set, right? We will get a set. We cannot rank them because all are satisfying the query, all of them. So they are actually equally, from the system perspective, they are equally relevant to the query. We cannot sort them. Okay, my typical example here is one where if you try now, if you have your mobiles, right? Try now to search Google, type QU, just search one word, QU, not Qatar University, QU, and see how many results you will get. The number of it, I don't know if the search interface on your phones will give you the number of results or not. We will see it. Did you get it? How many digits? 9 digits. Actually, more than 9, I think. 9? 1 billion. Okay, something like that. It's a huge number, which is the number of documents that have this word, by the way, on the web. At least the crude version of the web. Okay. Now, why I'm asking you for this? Imagine that now we do QU with Boolean retrieval. We'll get 1 billion page back. How will you do? What would you do with that? Okay. And imagine that you want for example, the homepage of Qatar University. Instead of giving you the homepage in the first result, I'll give you 1 billion page and tell you are welcome to go through this set and find out what you want. Of course, that's very bad. Type. Given what we just mentioned or what we discussed now, is that actually used or just a toy model that we started the course with? Yes.
I think it's like a start.
It's a start.
But
Start in what? In learning IR?
no. Maybe
It is actually.
maybe it is used, but then we perform ranking after that. Something like
Okay. You mean it's like a first step in ranking, in getting results. Okay. But that's not what I meant. What I meant by the question here is that is it actually used as a retrieval model in search engines, in at least some of search engines? Yes. If there is some modification? Oh, yeah, you mean more extensions? Okay, again, I'm asking about this exact thing. Right, let me change the question a bit. Did you see in your life, or did you use in your life, any search service that works like that? No, I'm not talking about database. I know that database is like that. That's okay. I will not upload the slides. That's really bad. I don't like that. Okay, thanks for letting me know that now. Okay. Yes. Okay, so but that's not a search. Yani it's just finding within a one word. It's not a search engine. Okay. In did you ever? I think you did. Did you ever use your? Did you ever search for specific emails in your email client application? You search for emails, right? Is that similar? It is exactly. It is exactly like that. Okay, so the search facility in email applications are actually using Boolean Retrieval. Why? First, the collection of emails is not that big. Thousands, but it's not that big. Okay, but that's not the main issue here. What is the main point? Why Boolean Retrieval is good for email search, but maybe not good for web search, regardless of the scale. I know that the scale is a difference, but aside from the scale, because in email you have in mind that there are some emails that you got that have this words and that word and maybe at that date. So you need exact match. So that's the actual task. The actual task is exact match. Okay, so that's one application. Another in what we call legal search. Okay, sometimes lawyers do search over collection of documents to get evidence from these documents. Okay, they need to really get some documents that have specific words because that will be a legal document. They want the evidence to have specific characteristics. Okay, so they want specific document out of this entire collection. So they also it is also usable in such applications. So the idea here is that it depends on the task. Okay, so some tasks actually require exact match. Okay. Yes. Yes? Can you raise your voice, please, because you are very far. In email. Okay. Did we say that we are done with Boolean Retrieval? We didn't. We are still talking about Boolean Retrieval, but we talked about the idea and the first implementation of it, which is the matrix. Okay? Stay tuned to the end of the lecture. Ask me this question again at the end of the lecture. Okay, now let's. Sorry. Okay. Should use this. Now let's do this together. Let's say that we have a collection which is 1 million. Yes, you have a question? Yes. Let me finish this slide and we'll go. Okay. Remind me if I didn't. Let's say that we have a collection of 1 million documents. Is that very large collection? First, it's not. In IR sense, it's not large. Right? It's a typical. It's a toy collection. Okay, but for us now, it's 1 million documents. Okay, it's 1 million documents. Now let's assume that each of them has about 1,000 words. And I like an article. I think maybe 2 pages or 3 pages. It's not that much. And let's say that over the entire collection, let's assume that it's in English, we have about 500,000 different words. Okay? We'll assume that the number of unique words are 500,000. Why do we care about this number? Because that will present to us the size of the matrix, right? The size of the matrix is what? Number of rows times number of columns, right? Which is number of terms times number of documents. Very good. Now, the 500,000 by 1 million, this is the number of rows and number of columns, matrix, has a, if you multiply these two numbers, you will get 500 billion zeros and ones. That's the size of the matrix. 500 billion. What is the trillion? Trillion is 1,000 billion, right? And the billion is 1,000 million. Just to get an idea. Okay, so 1/2 trillion is 500 billion entry in the matrix. That's the size of the matrix. So it's a huge size, right? Although the collection is not that big yet. Okay? But it's a huge size. Now, I'm claiming here, and I'm asking you for a justification, that it has no more than, the size is 500 billion, right? We said that. 500 billion. But I'm claiming here that it has not more than one only billion ones. Remember, the matrix is zeros and ones, right? Okay. So the size of it is 500 billion. But I'm claiming here that the number of ones, if we look at this matrix, the number of ones in that matrix is just 1 billion out of 500. Why? Yes. No, it's not about searching. The matrix has nothing to do with the queries. Right? If we will build such a matrix, will that be done online or offline? Offline, of course. It has nothing to do with the query. Okay? So remember always, if anything that is independent of a specific query, that will be done offline. Okay? We call, by the way, online, we call it also query time. Whatever we do at query time, this is what we call online. Okay, back to this question. Why is it 1 billion out of 500? I need someone who didn't answer before. Who is Tamer? You don't know. Okay. Tamer يعني عيب يعني. Okay. طيب. Yes. A question, not an answer. Okay, let's get back. We have ones here, right? Where's the query? We built the matrix. No. Building the matrix has nothing to do with the query, right? We built such a matrix. We did it together, right? Did we have any query? We didn't. Okay, back. Sorry. Huh? Did you look at the slides? Okay, yes. Give me, okay, I'm giving you a number, right? So it seems like there is a mathematical number somewhere. Tell me this and that will provide that number. It's not like, it's mathematics here. Yes. Maybe also. Maybe means maybe. I need an answer, a definite answer. Like what I got from Ihab earlier. Was very confident. Yes. Maybe برضو. Why is it maybe يعني? Okay. As maybe it means it might be true or false. I need an answer now. Why? What? Okay. The information is here, by the way. The information is already here. You should not say, huh? Very good. Okay, then. How is that related to the number of ones? Yes. Yes. Because we have 1 million documents and each has 1,000 words. No, why? Why should we multiply that? Yes. Okay. How is that related to number of ones? How is that related to the number of ones? I know that you, some of you noticed that 1 million times 1,000 is 1 billion. Okay, but why? Why? What is the meaning of that? Yes. Sorry. Yes. The number of words. Yes. How is the number of words related to the number of ones? Huh? Okay, tell me how you calculate the number of ones to be 1 billion in this case. You are very close, yes. Yes, you. Maybe, but if okay, yes. You raised your hand, right? No. Oh, him, yes. You did, right? Yeah, okay. Suppose. Assume, suppose, maybe, probably, possibly. Yes.
No more than 1 billion.
Yes.
That means the maximum I can get one document which has the 1,000 words.
Yes, because each document has 1,000 words. So every column, that's what I wanted you to say. Every column will have maximum of 1,000 ones because it has no more than 1,000 words, right? So if I look at every column, it will not have more than 1,000 ones, right? I have how many columns? 1 million. 1 million times 1,000 is 1 billion. No, we don't care. No, that doesn't mean that. Of course there are repeated words. Of course there are intersection between the documents, okay? That's at the row level. But at the column level, okay, each column will have 1,000 maximum. So 1,000 times 1 million is 1 million. Now why I'm asking you to do that? Because now compare the 1 million, now compare the entire size of the matrix, which is 500 billion ones. How many, 500 billion cells or entries, but only 1 billion of them, and 1 to 500. The number of ones is 1 out of 500, 1 to 499 zeros. Okay? How is that, or why is that a problem? It's mostly zero. Very good. When a matrix is mostly zero, we call it sparse matrix. Okay? Sparse matrix. And when we have a huge matrix that is sparse, of course it's not efficient to keep it as it is. Right? We cannot just keep it in memory as it is. So the matrix is extremely sparse, and there must be a better representation than that, which is what we will start with after the break, inshallah.